Hello, good morning or afternoon, whenever you're watching this. We are in week 3 of geometry, and we're going to be covering perpendicular lines. Okay, so first things first, we have some vocabulary. Perpendicular bisector theorem is the first thing we're going to learn. If a point is on a perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. All right, don't worry about necessarily what that means. Just go ahead and write it down because this is your vocabulary, okay? So that's the first thing I want you to write down. The second thing I want you to write down is the Pythagorean theorem. Now, notice this is the actual proper definition, so if it sounds a little wordy, I'm going to show you how to use it, but just for now, write down the definition. Pythagorean theorem is a theorem attributed to Pythagoras that the square of the hypotenuse of a right triangle is equal to the sum of the square of the two sides. Okay, so basically, what do these two things mean? Well, the first one, right, the perpendicular bisector theorem, right? What that's saying is if we have two lines and there is at least one right angle formed by making those two lines, a couple things happen, right? So if you remember from last week, a straight line is 180 degrees, right? A straight angle, do you guys remember this? A straight angle or a line equals 180 degrees. And if one of those degrees happens to be 90, there's only one number the other one can be. In order for that to work, the other angle next to it has to be 90 degrees as well. But then what if we want to know about the other angle, the one top and down? Well, the other line, if this really is a perpendicular line, then this will become 90 again, because 90 and 90 gives me 180 degrees. And the last angle is 90 and 90. If you have at least one 90-degree angle, you have what we call perpendicular lines, right? This means that all the angles across the four angles across the two perpendicular lines are all going to be 90 degrees. Now, this is important because we're using things from last week to kind of connect this. And you might think, is that it? Is that what we're talking about? No, that's not it. Perpendicular bisector theorem. The word bisector means two sections. Bi means two. Sector means section, right? Perpendicular means that there's going to be 90 degrees, right? So if you have a 90-degree angle, what happens is, right, let's draw a section. If you have a 90-degree angle like this and the lines are perpendicular, this line and this line are going to be the same. So if this is 5, this one's going to be 5. What if you have another one that's even longer, like this? This one's going to be something like 7. We're talking about the side here, not the angles anymore. This one's also going to be 7. Okay, I'll go into more detail what this looks like later. For now, I just want you to understand a little bit of what we're trying to do here, right? The angles mean that we have determined the type of sides, right? If you have certain angles, you're going to have certain sides, okay? Okay, what about Pythagorean theorem? Now, this is something that you guys might have remembered. I say might have because I don't know when was the last time you guys did this. But we're going to have another familiar looking symbol. We're going to have a little square inside that indicates a 90-degree angle, right? And this is going to be a triangle. This is what we call, remember how we a 90-degree angle was called a right angle? Well, if you have a 90-degree angle in a triangle, it's called a right triangle. Okay, seems pretty straightforward, right? The sides of the triangle vary, but I want you to write this down. The bottom part of it, this part right here, usually is referred to as side A. This one, the longer side, usually is referred to as side B. And the longest side, the hypotenuse, is side C. Now, A and B are what we call the legs of the triangle. And C is what we call the hypotenuse. I know I'm throwing a lot of vocabulary, guys, but just try to write this down in your notes. And we're going to get to all this in a second. The hypotenuse, another way of thinking about it, it's also the longest side. In a right triangle, it's also the diagonal one. I think I misspelled that. Anyways, it's the diagonal one, all right? So, okay, that seems like it's pretty background information. By the way, A and B are just labels for the legs, anything that's not the longest side of a triangle. You can replace them and you can replace them, like B can be A and A can be B. I'll talk more about that when we get to uh, the Pythagoras theorem. But just keep this in mind for now. This is how we usually label right triangles, okay? Okay, let's move on. Okay, why don't we slow down and why don't we talk about the perpendicular bisector theorem? All right, so here you have that familiar shape, right? And you're always going to have a given, right? In this given, it says that that's information given to you outside of the problem, right? In the beginning of a problem. So given just says that the segment DB is perpendicular bisector to segment AC. So if you notice, we have DB, right? It's this and this, right? DB is a line that crosses line AC, right? We have two lines that cross each other, and they are perpendicular bisectors. This is told to us. That's why there's a 90-degree angle there. But I don't want to put a 90-degree angle on all the corners, so I'm just going to put it on one of the corners, right? If you notice E, there's a letter E inside that shape, right? E is referring to the dot that's right in the middle. It's right where everything crosses. We're going to get to E in a bit, all right? So what does perpendicular bisector theorem say? Well, let's look at number one. Suppose ED. Now, E, again, is referring to just this center one. We're going to start there. E and D, this little segment right here, right? That little segment right there is, let's say that it's 16 centimeters, right? Let's just pretend it's 16 centimeters. And DA, right, this segment right here between D and A is 20 centimeters, right? Find DC. Okay, so according to the perpendicular bisector theorem, um, if something is perpendicular and you have lines from the 2 points, they're going to be equidistant from each other. What that means is AE is going to be equal to EC, right? AE is going to be equal to EC. Okay, so this is because it's a perpendicular bisector theorem. Okay, this is what the theorem says. Now, we don't have, because again, I'm sorry, I really do want to go into like why this is, and we're going to go a little bit into more in detail, but not that much. Normally, if we had more time, I'd have you derive this formula, but for now, you're just going to have to remember that they're equally distant. Okay, that's the easiest way I can make this. Okay, so according to the perpendicular bisector theorem, we also know that the opposite sides, right, are going to be essentially equal to each other. Right here under my explanation, right, I have an explanation right here. According to perpendicular bisector theorem, DA is also equal to DC. DA, which is going to be equal to its counterpart, which is on the other side, it's on the right side, happens to be DC, according to the perpendicular bisector theorem. Now, if we know that DA is 20, that means that DC has to be the same thing. According to this theorem, it's 20, okay? So because they share a perpendicular bisector, we know that DA is 20, then DC has to be 20 as well. That's what the theorem tells us. The theorem is kind of a shortcut. You want to think of the theorem like this. Instead of having to prove that AD is DC every single time by doing a bunch of math, the theorem just says if we have this specific situation, then one thing is going to equal the other every single time, okay? That's why it's important to memorize these things, because then when you see them, you can be like, oh, well, that has to be equal to that. Why? Because of the theorem. It's easier to explain that way. Okay, so number two, suppose that EC is 15 centimeters. Well, EC, right, Suppose that AC is 15 centimeters and BA, right? BA, this is 25 centimeters. Now I know that AD is 20 and it looks like it's bigger than AB, but just ignore that for a second, right? These two problems are separate problems. In the second problem, again, we're supposing that BA is 25 centimeters, right? Okay, they want us to find BC. Now we have to think. Okay, BC is a counterpart to either EC or BA. Well, remember they have to share a perpendicular bisector. EC doesn't share a perpendicular bisector with BC. Not really. They're not the same segment. However, AD and AC is the total line, and it's cut in half by DB, right? So that means that to the left of DB and to the right of DB are going to be their counterparts to each other, right? So if we want to know which one it equals to, BA is going to be equal to BC. Now, how do you know that they share a perpendicular bisector? How do you know that they're going to be equal to each other? Well, if you notice, they have something in common, right? They have that B in common, right? And we know that BD, that B is part of the perpendicular bisector. That's what I mean by like they kind of share one, right? They have something specifically in common, which means that they're going to be 25 as well. This is me just using the perpendicular bisector theorem. That's all I'm doing. I'm just labeling, and I'm just figuring out which one is going to be the same thing as the other one. Okay, that's it. Okay, I want you to pause the video and make sure you have all this. And then we're going to switch gears and we're going to explain something else. This is the first concept. We're going to explain a second concept. The second concept is the Pythagorean theorem, okay? Now, I've already said this before, but if you notice to the left, right, we have a triangle, and we have ABC on the triangle. We also have a 90-degree triangle. This is a right triangle because it has a 90-degree angle. If you're wondering what that is, whoops, okay. That little square means that it's 90 degrees. So if we have at least one of those in a triangle, it's only possible to have one of those in the triangle. But if we have one of those, then this is a right triangle, right? This means that its sides have special rules due to the Pythagorean theorem. Meaning that if we know at least two of the sides, that means if we know at least two of these variables, right? The variables are A, B, and C. If we know A and B, we can figure out what C is. If we know what C and B is, we can figure out what A is. If we know what C and A is, we can use Pythagorean theorem to figure out what B is, the missing side, right? Okay, so what is the formula? Well, the formula is right here. You see what I just circled? The formula is, the Pythagorean theorem is A squared plus B squared is equal to C squared, okay? Now, with this in mind, we're gonna have to plug in numbers, right? In order for this to even begin to make sense. So what this means is if all the conditions are met and we do have a right triangle and we know two of the sides, we can figure out the last of the sides. In our example here in the problem that we're going to do, we're going to say that A is equal to 3, B is equal to 4, and we're trying to figure out what C is. So we're going to move down here and we're going to use the formula. We're going to start with the first step, which is write down the formula. A squared plus B squared is equal to C squared. And then we're going to, right, that's the formula, check. We're going to move on to step 2, right? This is step 1. This is step 2. Step 2 is substitute values, and then we're going to square the values, right? So from here, we're going to substitute for A, we're going to replace it for 3. Why? Because it's part of the problem, right? This is part of my given. This is information that was given to me in the beginning. We know for a fact that A happens to be 3 and B happens to be 4, right? We're trying to figure out what C is, and we're going to use the Pythagorean theorem to figure out. So let's plug in 3 for A. 4 for B. Now, if you notice, I put them in parentheses and I put a square on the outside of it. That's because the square doesn't affect them just yet. All we're doing is we're replacing them. We rewrote the formula, and now we're going to move on to step 3. Okay. Okay, step 3, we're going to add like terms. Now, remember when I said square it, right, in step 2? That 3 squared became a 9, and that 4 squared became a 16. I'm going to direct your attention to this side here. This is what I really did. When I say 3 squared, what I'm really trying to say is we're going to multiply whatever number is being squared by itself 2 times. That means 3 times 3. So 3 squared is the same as saying 3 times 3, which is the same as saying 9. 4 squared is the same as saying 4 times 4, which gives us 16. So that's where I get it. I'm just plugging in these numbers down here. Okay, that's all I did. All right, I just showed my work separately. Okay, so now for step 3, I'm going to add like terms. Notice, if you notice, I haven't done anything to c squared. For the first steps, 1, 2, 3, c squared was kind of just there, and it keeps coming down. That's it. Because I don't know what to do with it yet. But I figured out the left side of the equation because that's where my 2 regular numbers are. So I have 9 plus 16. The plus is just part of the formula. Okay. Now, 9 plus 16 is going to be 25. And I end up with 25 is equal to c squared. Now, we're moving on to step 4, which is square root both sides, because I have a problem here. If I have c squared is equal to 25, right? Maybe I should write it over here. This is what I should have ended up with. I can't leave it like that. This square right here is a problem. In order for me to get rid of that square and figure out what just c by itself is, I have to do the opposite of a square. I have to square root, right? That's where this little house comes in, this little symbol. Now, what's really going on when I square root something, right? In case I haven't explained this, it's that the number that's being square rooted, in this case, number 25, I have to figure out what number multiplies by itself to give me 25. All right, one number multiplies, this is a multiplication symbol, to give me 25. Whoops. Okay, well, there's only one number that can do that, 5. Because 5 times 5 gives me 25. So if I square root something, I take one of these, and that's my answer. All right. You can use your calculator to solve this, right? If you find that simple, if you're using an Android calculator on your phone, right? If you have an Android phone, be sure to put the symbol first. Find the symbol. Move your phone sideways if you have to. It'll give you more options depending on your model, right? Find the square root symbol first, which is that weird looking division sign, and then put the number 25, and then put equal, and it should give you 5 as your answer. If you're using an Apple device, move your calculator to the side, move your phone to the side, and you should get a bunch of options. You're going to put the number 5 first, then you're going to look for the symbol that looks like that. If you're using an Apple device, your symbol could look like this, right? It could look something like that, just letting you know it's the same thing, okay? You find that, and that's how you would square root. Okay, so this is the Pythagorean theorem concept. This is concept number 2. All right, we're almost done, guys. Let's combine these 2 concepts. We're going to combine the perpendicular bisector theorem and the Pythagorean theorem to solve a problem. This is what you guys are expected to do throughout this week, right? So if you notice, I have a very familiar looking triangle looking thing. And I'm going to say, given the line segment DB is perpendicular to line AC, all I'm doing with the given is setting up that this is a perpendicular bisector. Therefore, we can use perpendicular bisector theorem, all right? Now, the problem says that AD, right, is 10 inches long. BD, right, is 6 inches long. Find AC. The objective of this problem is to figure out what that whole thing is, right? Now, if you notice, AC is broken up into segments AB and BC. And according to perpendicular bisector theorem, they're going to be this AB and BC are going to be the same thing. Why? Because they share B, right? So let's go ahead and undo that. All right, now I have an explanation of the problem here. Since we see a square inside the shape, we can assume that there's at least one 90-degree angle, meaning that the lines are perpendicular. That's just explaining the given. The problem is asking us to find AC. However, even with these two concepts we learned, we cannot do this directly. So we will have to break this problem down step by step. We can use the Pythagorean theorem to find the missing side of one of the two triangles, right triangles. Then we can use perpendicular bisector to double our value. So what we're going to do is we're going to use, right, Pythagorean theorem to figure out one of the sides. Now, we may not know all the sides of the triangle, but we can see that there's two right triangles, right? I'm gonna redraw the triangles over here, right? A, B, and D is one of the right triangles. D, B, and C. That's the other right triangles. All I did was I just separated them. I happen to know that they're both right triangles, and this is 10, this is 6. I'm trying to figure out what A is, little a, right? I also happen to know that this is the same as that, right? Okay, so what am I going to do now? I said I was going to use Pythagorean theorem, so that's what I'm going to do. I'm going to direct your attention down here now. I set up my equation first. A squared plus B squared is equal to C squared, right? This time, however, I'm looking for A, so I'm going to leave A blank. A squared plus 6 squared is equal to 10 squared. Why? Because the longest side, the hypotenuse, the biggest side, AD, is 10. This was given to me. So this Pythagorean theorem solution is going to look a little different from the last one, right? I'm still going to square what I can, right? So the next step, step number 3, a squared plus 36, because 6 times 6 is 36, is going to equal to 100, because 10 times 10 in the previous step is equal to 100, right? I'm right here. Okay, so problem, what am I going to do? Because I have a squared on one side and it has a number. How am I supposed to add? Remember how last time I just added? Well, I have to isolate A, right? You have to remember from your algebra skills how to isolate a variable. And the best way to isolate a variable is to get rid of the non-variable. In this case, it's 36. We have a plus 36, so I have to do the opposite. And if you notice, I'm subtracting 36 from both sides. So now, when I subtract 36 from both sides, 36 disappears here. And when I subtract 36 from 100, I get 64. So I have a squared is equal to 64. Remember, the square is the problem. I have to get rid of it. The opposite of a square is a square root. So I'm square rooting both sides. I have a squared square rooted is equal to square root of 64. Now, as you guys remember, the square root of 64, there's only one number. There's only one number that multiplies by itself to give me 64. That's 8. So that's what I'm going to put. Or you can just use your calculator. A is equal to 8. Okay, so am I done? Do I know what it is? No, because look, all I did in the original figure was figure out that this bottom section was 8. According to the perpendicular bisector theorem, however, we know that if AB is 8, BC is also going to be 8. Okay, but how does that help me? I mean, I was trying to figure out this entire time. The problem is asking me to find the length of AC. Well, now that I've used the perpendicular bisector theorem to figure out what BC is, right? The perpendicular bisector theorem, I'm going to just label it as PBT, says that AB is equal to BC, so they're both 8. Therefore, AC, the whole segment, AC is equal to AB plus BC. And if we know that AB and BC are the same, they're both 8, I just have to add 8 plus 8. AC, the thing we were looking for this entire time, is 16. Okay? And that is what you will be expected to do throughout this week. Problems like these. Now, I can already hear some of you saying, well, I've looked at some of the problems and I'm confused because the problem doesn't look like this. It looks more like this. All right, this is the last slide, I swear, guys. Okay, a slightly more complicated version of the previous problem, right? This case, you have two triangles, right? And they're kind of, one is kind of inside the other. It's like, it's got this weird thing going on, right? You guys can do this, all right? We're gonna do the same thing. However, we're gonna reverse the order in which we do the steps. So you have to learn to adapt your steps based on what the problem is asking you. For example, here, it says given that BP is perpendicular bisector to AC and QC is a perpendicular bisector of BD. So if you notice, there's two perpendicular bisectors and there's two segments that we need to pay attention to because there's two triangles, right? All right, so what is the problem asking me? It says if AC, right, is 12 and QD is 12, what is QC? All right, why don't we go ahead and label what we know? We know that from here to here, right, it's 12. We also know that QD is 10. What we want to know is QC. This is what we're trying to figure out. All right, we can do this, all right? Connections that need to be made, right? Now, here I just wrote out what I just basically just said, right? But we need to make a couple connections here. Now, according to perpendicular bisector theorem, PBT, we know that AC is made up of AB plus BC. And we know that whenever you see this symbol, guys, by the way, you see how there's like a single line, and a single line there? What that says is that each and every one of those segments are equal to each other. So even though they didn't tell us in words, they told us in the symbols in the problem that AB is equal to BC, which is equal to CD, right? Each and every one of those sections is equal to each other, right? So what I have here is that AC is equal to AB plus BC. And we happen to know that AC is 12, which is why I replaced AC with 12 in that equation, right? Is equal to AB plus BC. But we don't know what either of those are. So I'm going to replace those sections with the same variable. Why? Because I happen to know that they're the same thing. What I mean by that is if these segments are all the same, I can put the same variable to represent each and every one of them, right? That's supposed to be an X, sorry. Okay. So that's why I made AB into X and BC into X, right? So 12 is equal to X plus X, which is 2X. And now I have to get rid of, you know, the coefficient 2. And since 2 is multiplying by X, I have to do the opposite, which means I have to divide by 2 on both sides. So that 12 gets divided by 2, and the 2's cancel out. So I'm just left with regular X is equal to 6, which means that AB is actually 6. And BC happens to be 6 as well. So now that we know what each segment is, how does that help me, right? I'm trying to find out what QC is. Well, really what I'm trying to do here is I'm trying to actually figure out what CD is. Because if I can figure out what CD is, guess what? I know that I have a right triangle that I can use. QCD makes up a right triangle. How do I know there's a right triangle there if they didn't give me a little square? Well, remember, they said they're perpendicular bisector. So that means that implies that there's a 90-degree angle right there, even if they don't tell me it is, right? So what can we do? Well, why don't we go ahead and relabel some stuff, okay? Let's see, do that. And we know that this is a 6 now. And we know that QD is a 10. And if we take this triangle, right, redraw it right here, we know that this is Q, we know that this is D, and we know that this is C. We happen to know that this is 6 now, we know that this is 10, and we're trying to figure out what this is. We know that this is a right triangle, right? So now using everything we've learned, why don't we relabel this triangle into A, B, and C? The bottom one, A, the part we don't know, B, and the longest side of the triangle, C. Okay, now that we know this, we can use Pythagorean's theorem. A squared plus B squared is equal to C squared. I'm just going to replace it with everything I know. And this kind of looks like the last problem, right? Actually, it looks exactly like the last problem. That right down to the actual math of it. And you're going to see that this is a pattern in a lot of like uh, right triangle problems. There's only so many perfect right triangles. So once you start seeing the pattern, you'll be able to solve this without even using the formula. But for now, let's go ahead and do the math. 6 squared is 36 plus b squared is equal to 100, right? I'm going to subtract 36 from both sides. I end up with b squared is equal to 64. And I square root both sides. B is equal to 8. And again, what was b again? Well, another name for b was side QC, which was exactly what we were looking for the whole time. QC is equal to 8. All right. So if you notice, the difference between this problem and the problem before it was in the order in which we used what we knew. In this problem, we had to make the connection, right? We had to say something like use the Pythagorean theorem first, right, to complete the triangle, and then we use perpendicular bisector to double our answer and get the right answer. Here we had to use the perpendicular bisector theorem first, and then we use in order to complete the information we needed in order to use the Pythagorean theorem. So you're gonna have to know how to do this both ways, right? Good luck with the work, and just know that after the end of this week, you're more than halfway done. So good job. See you guys.